Hello! Today, this is part 2 of my videos on systems of equations within Further Maths A-Level, and therefore I'm assuming if you're watching this video you already either know all the stuff that I covered in part 1, or even better, you've actually watched my part 1 video, and if that's not the case, a link to the part 1 video is appearing on the screen right now, and if it isn't, just go to my channel page and find it because it's only just a little bit before this video was released. So with that said, what were we trying to do last time? A reminder, we were basically trying to solve or look at simultaneous equations, specifically for Further Maths A-Level, triple simultaneous equations with 3 variables. And we weren't just looking at solving them though, because instead we were more interested in deciding how many solutions the simultaneous equations had, whether the system of equations was consistent or inconsistent, and then also identifying the geometrical configuration of the planes, which is basically a posh way of saying if you were to draw a graph to have a visual representation of the equations, what's going on. The other thing to remind you about is what does the word consistent or inconsistent even mean? Inconsistent basically means no solutions at all, and therefore consistent is the opposite of that, so it means there are solutions of some variety. No idea how many of them, that doesn't matter. It could be 1, could be 2, could be 10, could be infinite, but just there are some solutions. And the way of determining all this stuff was by doing a bunch of little sort of checks, if you will, and this could be represented using the flow diagram you can see on the screen right now. Because we realized it's a big flow diagram, decided to only focus on this stuff at the top in part 1, and therefore logic states. We're going to be looking at the stuff at the bottom in today's video. And I guess the next thing to also point out is that students, therefore, when they see this flow diagram, tend to either freak out about this stuff sometimes, or just later on they sort of have a mental block on this stuff because they're like, oh my goodness, I can't remember everything in the flow diagram. But therefore, the thing to bear in mind is that actually everything in this flow diagram is boiling down to sort of 3 checks, if you will, and none of the checks are that involved, not that long. And ultimately, the other thing that students sometimes have a problem with, therefore, as part of that is not just remembering the checks, but also the order that they're meant to do them in. And the thing I'd say about that is that actually there is no mathematical reason we have to do them in the order that I show you them. However, there is a tactical reason you'd want to do them in the order you do them in, and therefore that can help you remember what order to do them in. It's basically just the order in terms of how much time it takes to do each of these checks. We start by always checking whether any of the planes are parallel or not, because that's the quickest thing to do, because it involves just looking at the equations and just spotting, are the coefficients of one equation going to be the multiple of the coefficients in another equation? That's something you can do just by looking at it, so therefore it's really quick to do. That's why you want to do it first, because there's no point doing the longest step first, and then after doing all the effort, you find out, oh, wait a minute, the planes were just parallel along, and I just wasted loads of time. And that's why we also, if you then find that none of the planes are parallel, we then check if the determinant of the matrix of coefficients is equal to 0, because that's like the second quickest thing to do, because it's something you can just type into the calculator, and therefore it's very quick to determine. However, if after that you determine that the determinant of the matrix of coefficients is equal to 0, yes, then that is where we got up to in the last video. So we now need to cover what happens beyond that stage, which is where we're going to now look at the third check that you need to be looking for. There's sort of 3 main stages to doing this, and actually the first one is actually a very common idea that you've been using anytime you need to solve simultaneous equations yourself manually. You basically take one of the equations and you rearrange to make one of the letters in that equation the subject of the formula. And then you substitute that into the other simultaneous equations. Now, if you just have 2 simultaneous equations, that previously meant you were just substituting into one other equation, but because we've got 3 equations in total, that means we've got 2 other equations to substitute into. But anyway, looking at that as an idea, let's look at an example. And this, funny enough, is the example 2 that we looked at in the part 1 video, because we already decided by looking at the coefficients of each equation, none of the coefficients are multiples of the coefficients in another equation, so none of them are parallel. So that's the first thing we had identified. We also already identified that the determinant of 2, 1 minus 1, 1 minus 5, 4, 42 minus 1 minus 3, the determinant of the coefficients of the x, y's, and z's in those equations, was 0. So that's why we're ultimately at this stage in the process, because we'd already eliminated the other possibilities. So therefore, we now can move on to actually doing stuff. So first of all, I'm going to label equations. And then that means I can start by choosing one of these equations and making one of the letters the subject of the formula. It will work no matter which equation you pick and whichever letter you pick, but be tactical. It makes sense to pick a letter that you currently only have one lot of, because that means then you don't have to divide by a number as part of the making that letter the subject of the formula, which means you can avoid fractions, which, you know, it's not like you can't deal with fractions, it's just that it takes longer to deal with them, so best avoided. So therefore, I'm going to be tactical. I'm going to rearrange the first equation to make z the subject of the formula. So therefore, a would get rearranged to, well, the easiest thing we'd do is just add z onto both sides to move it onto the right hand side, and then take away 5 from both sides to get 2x plus y minus 5. And so now we're going to substitute that into the other two equations. So first of all, doing that to b, we will get an x, a minus 5y, and then we were having a plus 4z before, but now we're replacing z, so now we've got plus 4 lots of 2x plus y minus 5, and then we got the equals 1 on the end still. And now we just got to do some simplification. So what we want is we're going to end up with x minus 5y plus 8x plus 4y minus 20 equals 1, and I'm going to gather all the x's together, so that means we've got 9x, we've got a minus y, and moving the constants over to the other side, we get positive 21. And then I'm going to do the same thing with the other one, so I'm going to sub a into c, and therefore we'll have 42x minus y minus 3 lots of 2x plus y minus 5 equals, in this case, 0. And then doing some simplifying there, we're going to end up with a minus 6x, we're going to end up with a minus 3y, a plus 15. Ooh. And then, therefore, simplifying that, you're going to end up with a 36x, a minus 4y, and we could move the 15 on the other side to get a minus 15. Now, the next thing you are going to want to do is you're going to try to simplify both of these equations you've got up until the point where you've got the same multiple of or not even multiple, the exact same coefficients for your remaining two letters. So for my two equations, I've got x and y, and therefore I want to get to the point where both these equations have the same number of x's and the same number of y's in between the two equations. So therefore, you'll notice that that's actually going to be quite easy to do, because this equation at the bottom, I could just divide both 36 and minus 4 by 4, and you will get 9 and minus 1. So therefore, I'm going to divide this whole equation, this second equation we've got, by 4, because then I'll end up with 9x minus y, and we've got to do the same to both sides, so I've got to divide the right-hand side by 4, and that'll get me minus 15 over 4. This should always be possible to do, by the way. You should always be able to get it so you've got the same number of, in this case, x's and y's in both of our equations, but whatever two letters you've got left over, the same number of those two letters in both your remaining equations. If that is not possible, then you know you've either forgotten to check whether any of the planes were parallel or the same before you started, or you have made a mistake with your algebra. So I must admit, I've seen actually a few different ways of approaching this part of the checking before. It all involves basically, you know, some sort of algebra and plugging stuff in, but this sort of very set way I'm doing it is good, because it means you have a nice easy way of knowing if you're on the right lines or not. So we managed to get the same number of x's in both equations, the same number of y's in both equations, therefore I know things seem to be going all right so far. The last thing you need to do once you've done that is you then need to look at the constant term, the number that's left, I've written it on the right hand side. You need to check, is that number the same in both equations? Yes or no. So in my equation, I got to the point where they both have 9x, they both have minus y, but then the number on the end, one of them has a 21 and one of them has a minus 15 over 4. All that's going to then tell you to do is to then realize that if they do have the same coefficient on the end, then it's infinite solutions, they're consistent. Whereas if it's no, then in which case there's no solutions and they're inconsistent. This is where the words consistent and inconsistent do start to make sense in the context of what we're dealing with, because for our particular example, we had a situation where basically the two equations are not agreeing with each other fully, so therefore they're not consistent with each other from what the word consistent generally means in the English language. So therefore we can say for our particular situation there's no solutions, it's inconsistent, so therefore we can say these two equations are inconsistent, there are no solutions. And then when it comes to the geometrical configuration of this, it's what we call basically the three planes. You might have seen on the other side, the three planes form a prism. Now that is the part you are going to need to just remember. So out of all the parts, that's the part that does take a bit of revision, but it still makes sense logically. What's going on, if you want to look at this visually, is if you look at the plane side on, so the thin side is facing you, so to speak, this is what it kind of looks like. You basically have each pair of the planes intersecting, but there's no point that lies on all three planes at the same time. So that's what's going on, and then sort of, because the planes are facing towards you, they're heading towards you and heading away from you, so that's why you got this prism shape, because this triangle sort of thing ends up forming a sort of triangular tube, if you will, in the center. Cool, so that's one example. Let's do a second example to see situations that might involve consistent solutions. So therefore, here is our other example. First thing you need to do is check, are any of the planes parallel or not? So have a look at them. The first and the second equations, they don't have coefficients that are multiples of each other, so therefore they are not parallel. The first and the third clearly aren't parallel either, and then the second and the third are not parallel either. So none of them are parallel. You don't need to write that down, by the way. I did last time. That was just to make the point that you do check it, but you don't actually need to write it down. Then the second check we do is you do need to do the determinant, and I will write that down. It's a good idea to do that. So we're going to do the determinant of 5, minus 2, minus 9, minus 2, 5, 12, and minus 1, 1, 3. If you type that into calculator, you will find out that the determinant of that is 0. Surprise, surprise, because that's what we've been dealing with in this video. But there you go, good to check, good to point it out. So therefore we're now on to that third stage, which is labeling the equations and then choosing one of them to make one of the letters the subject of the formula. I am going to choose the bottom one because that will be the easiest to do. So therefore for C, we can move the x over to the other side, and therefore we have y plus 3z minus 1 equals x, and therefore we can substitute that in. So I'm going to sub C into A first of all, so therefore we'll have 5 lots of y plus 3z minus 1, we'll have a minus 2y and minus 9z equals 7. And now we're going to do some simplifying. So just working through the maths, working through the algebra. We have got a total of 3y, we've got a total of 6z, and then we've got equals 12. Now, you might notice already that all the things in this equation could be divided by 3, so you're welcome to simplify this equation further. I'm not going to be bothering though, because sometimes that's wasted effort, and you'll see why in a bit. So now, substituting C into B. Now I'll repeat that process, so now we've got minus 2x, but that's now replaced with y plus 3z minus 1. we've still got that 5y, that 12z, and apparently that's equal to 14. So that will then multiply out the brackets. We will then gather the like terms together. So we've got a 5y take away a 2y. Oh my goodness, it's a 3y. We've got a 12z take away 6z, which is 6z. And then lastly, we've got the 14 take away 2 to get, what do you know, 12. So once again, we have managed to get to the point where we've got the same coefficients for the remaining two letters in both equations. And therefore, all we've got to do is check the numbers on the end. Are they the same or are they different? Well, this time they were the same. So therefore, we can say there are infinite solutions. And therefore, they're consistent because there are solutions. And also makes sense. The equations are literally agreeing with each other because they're literally the same equation. Therefore, they're consistent. And then, therefore, the geometrical configuration you might have just seen on the slide before is saying that the three planes form what we call a sheaf. That's sheaf spelled S-H-E-A-F, not sheath with a TH on the end because that's something completely different. That's a sheath with a T and an H is what you would store a sword in, where a sheath is like, well, something you could keep bundles of things in. It's kind of, well, it's another name almost like for a bundle, I guess, in some ways. What does that look like? Well, basically, if you look at the plane side on again, at the thin side, basically all three planes are crossing in the same place. However, that won't be a single point this time. That's why it's infinite solutions. It's not a single point. Instead, what you've got to imagine is, imagine you placing your pen at the point where these three, what appears to be lines, they're planes. Place your pen where that point is and have it facing towards you, and basically that's basically the three planes are intersecting all together along a line, and that line is where your pen is. So there you go, that's the geometrical configuration. And so the last thing I'd like to do is once again reiterate that when you're doing this stuff, the thing you need to watch out for is when you're trying to get the coefficients of the remaining two letters in the remaining two equations the same as each other, then if that's not possible, then you have either forgotten to do the very first step of checking if any of the planes are parallel or not, or forgotten to check if there's unique solutions, or you've made a mistake with your algebra. There is no situation that won't be covered by one of those things. So just watch out. Therefore, if you follow along in the way that I've been doing very carefully, you should always find it's possible to get the two equations having the same numbers of x's and y's or z's in each other, so that you can then just directly compare the constant term at the end. Nice. So that will do us for today. Hopefully you found this stuff useful. As I mentioned, it's very easy to get overwhelmed by this stuff, and actually I should just show you the flow diagram one last time in case you want to look at it as a whole. But that is it for today's video. Hope you found it useful. I will see you in a future video. Goodbye.